Okay, Dorota, we are looking forward to listening you.
Okay, okay. I would like to speak about mutual divisibility problem in graphs. This concept is very young, has only 3 years, but is related, is kind of invariant of the mutual visibility problem in general, classical one, and with the general position problem. These concepts in general are now in the last 5-10 years intensively studied. Uh, and this is one of the reasons that I would like to speak about that. Here we have no very direct, very strong relation with domination. We can have, there is some relation, and I will explain little after, when I will give some definitions. This concept is more related with distances in graphs, but I think that is good to speak about that, to know a little more about this concept. Mutual visibility problem in networks is very well-known problem in the area of computer science. Why is the reason of that? The reason is the connection with mobile robots that navigate in a network, avoiding collision between them. So we can understood this problem in the way that we have two robots and we would like that they will be mutually visible. Mutually visible, what does mean? We can mutually visible, we can understand like that. We will find between these two robots a shortest path, a shortest path in the network, such that there is no any more robot located in this shortest path. There are several different approaches to the problem. Sometimes visibility properties are understand that we want that for any two robots, we will have that all shortest path between them are have this condition that there are not located any other robots. And in this sense, if we consider all the possible shortest path and that this condition will be fulfilled, then the problem is called the general position problem. There are other different approaches, and after in some moment I will speak about them. Since general position problem is oldest that mutual visibility problem, I will start with define this problem, this concept, give I will first start with the definition of general position sets. So we have a graph G, and we are looking for the subset of vertices such that no three distinct vertices on each of this subset lie on a common shortest path. So for any, if we will take two vertices from this subset, then we will and we will look for all shortest path between them. In any of the shortest path, we will find other vertex from this subset. The idea is that we are looking for the maximum possible cardinality among all general position sets, because of course we can I'm sorry, of course we can tell if will be not maximum with two vertices we are done. So the idea is that we are looking for the maximum possible cardinality of this of general position set. And maximum possible cardinality we call general position number and denote by GP of G. We call GP set a general position set of cardinality GP of G. One example. Here we have a graph, and we can observe that these three red vertices form general position set. Why they form a general position set? Because between these two vertices there exists only one shortest path, and we can observe in the middle we have no any red vertex. So fine. Between these two vertices we have two shortest paths. Here we have one and here the other one, and both of these shortest paths have no more red vertices. And the same is happening here. For these two vertices, there exists only one shortest path, and we can observe that there is no any red vertex. So these three red vertices form general position set. But maybe we can find a general position set for this graph with more vertices, formed by 4 vertices, for example. So if we will observe this set of red vertices, we can also check that this set is general position set. We can find a bigger one with 5 vertices. If we will start to study, we will observe that no, because if we will start to add here some vertices or change one by the other one, then we will have problem. For example, if I will add this vertex, then the shortest path between this and this vertex, here is one shortest path, but here is other one. If I add this vertex, then for this shortest path, I will not fulfill condition of general position set. So here we have a general position number equal to 4. Mutual visibility concept problem is related with general position set, general position problem, as I mentioned before. This concept was introduced in 2022. And as I mentioned before, in this case, we are taking care only of one shortest path. So we are looking for of the subset of vertices such that any two distinct vertices from this subset have a shortest path joining them, such that this shortest path not contain any other vertex from this subset. And like in the case of a general position set, also here we are looking for the maximum possible cardinality of mutual visibility set. And this maximum possible cardinality we denote by mu of G, and we call mutual visibility number. The set which has a cardinality mu of G, we call mu set. So we will consider here an example, the same graph which we have seen before. In this case, of course, since these are three vertices form a general position set, so also these vertices form mutual visibility set, because mutual visibility set has softer condition. We need only one shortest path such that will not contain any other vertex from mutual visibility set. Then the same like in case of general position set, we will obtain here that mutual visibility number is equal to 4. We cannot find any subset of 5 vertices that this condition here will be fulfilled. As we can observe, we have here a graph that these two numbers are equal, mutual visibility number and general position number. This one can happen in several cases. We can imagine graphs where we have between any vertices, between any two vertices, only one shortest path. For example, path graph. In path graph, we have for any two vertices, there exists exactly one unique shortest path between them. So these two parameters will be equal. The same is happening in the cycles of odd number. And there are more graphs with this condition. So I would like to show now the graph where these numbers are different. Here we have the example. We can consider grid graphs. If a grid graph is Cartesian product of two paths, if we will consider that paths, both paths has at least 4 vertices, then a general position number for this kind of grid graph is equal to 4. We cannot add here more vertices. Why we cannot add? Because, for example, for these two vertices, we need to observe all shortest path, and all shortest path cannot contain red vertices. So this is the reason that we cannot add any more vertex. And this one will happen for any grid graph grid graph with at least 4 vertices. So we will have 4 paths for any grid graph where path has at least 4 vertices. So we can consider Cartesian product of paths with 2 paths with 5 vertices and so on. And always we will have a general position number equal to 4. In the case of mutual visibility number, the situation is really different. Since the condition is softer, we need to have only one shortest path that will not contain red vertices. Between 2 red vertices, we need to have one shortest path which will not contain. So since this condition is softer, we can add here more vertices. If we consider grid graph, in this case, Cartesian product of path P4 and other path P4, then we can observe that mutual visibility set can have 8 vertices. Because here, if we will observe, for example, between these 2 vertices, there are several shortest path, but we have at least one here, and even second, that does not contain wide vertices, vertices which are not, contain only wide vertices, vertices which are not belonging to the mutual visibility set. In the case of mutual visibility number, if we will do bigger grids, then this number will be bigger. Here we can see construction, how we will proceed, and which vertices can belong to the mutual visibility set. Here we have two very simple remarks. The second remark I explained before. In general, if we have a graph where between any 2 vertices we have only one unique shortest path, in this case, mutual visibility number and general position number are equals. Of course, in this group of graphs belongs also trees. And in general, we have this relation between these 2 parameters. Before continue, I told that I will tell where is relation with domination. So if we will see the definition of the standard mutual visibility concept of the mutual visibility set, then we can think that for any 2 vertices from this set, they control shortest path. So in some sense, we can think that they dominate this shortest path. They don't want to have in this shortest path more vertices from this mutual visibility set. Is enough with these 2. And as I mentioned before, this concept in general is more related with distances in graphs. Now I would like to speak about one of the invariants of mutual visibility problem. The talk is not about this invariant, but this invariant is very important and helpful to prove several things. The reason of introducing of this invariant was that these 4 researchers, they were working with a mutual visibility problem, with standard mutual visibility number, and they were trying to obtain some results for the Cartesian product of complete graphs. And when they were working on that, they noticed that they need one more invariant. They need the version where mutual visibility set will be total, in the sense that the condition which we have for any 2 vertices of the mutual visibility set, now we have the same condition, but for all vertices from the graph. So here we have the difference. Not only we consider any 2 vertices from this set, but also we consider vertices which are outside. And then we want that between any two distinct vertices, we will find a shortest path joining them such that this shortest path not contain any other vertex from this set. And of course, we are looking for the maximum possible cardinality among all total mutual visibility sets. We denote this cardinality by mu sub t of G, and we call total mutual visibility number. Here we have example for this case, for this invariant, the same graph which we have seen before. And then when we will observe these three red vertices, we will check now if these three vertices form total mutual visibility set. So we know that this condition for the vertices from the when these both vertices belong to the total mutual visibility set are fulfilled, but now we have to observe for all vertices. So for example, we can observe what is happening between these vertex for these two vertices. These two vertices are joined by two shortest paths. One is here, and this one is not good for us because this shortest path contains vertex from the total mutual visibility set. But there we have alternative shortest path, which is here. And in this path, we see that there are no red vertices. So it's fine for this case. We, of course, need to observe two vertices, which one is red, one black, if this condition also is fulfilled. So if we will observe here, everything is fine. But if we will try to form total mutual visibility set by these four vertices, then we will observe that we have problems. For example, for these two vertices. These two vertices are joined by two shortest paths. One is here, which has length 2, here is other one. And both this shortest path contains other vertices from the other red vertices, contain red vertices. So this one is not total mutual visibility set. For this graph, if we will check everything, we will obtain that total mutual visibility number is equal to 3. There are several different invariants of total mutual mutual visibility problem, of the classic mutual visibility problem. I will only mention some of them, but nothing more, only mention what you can find in the literature. To speak about these invariants, I need some definition. I need definition that two vertices are equivisible if there exists a shortest path between these vertices in graph G, whose internal vertices are not in this set. So if we use this definition, definition that two vertices are equivisible, then we can tell that mutual visibility set is a set where every two vertices from this set X are equivisible. Total mutual visibility, we have set which is total mutual visibility if any two vertices of the graph are visible. Other invariant is after mutual visibility set. The first condition is like in a classical mutual visibility set, and the second condition which we have that one vertex from the X and one vertex from the complement of X, they have to be equivisible. Other variety of other invariant mutual visibility set. So the first condition like in mutual visibility set, and the second is that for two vertices which are outside of this subset X, they need to be equivisible. There are more invariants. There is also independent mutual visibility set. So the set that fulfill this condition, classic condition, and also this set should be independent. Now I would like to speak about mutual divisibility problem. This problem, the reason of and motivation to introduce this concept is very practical situation. If we are thinking about networks, then many times networks are very large, and we have in some sense limited visibility. So if we are thinking about robots in these networks, they can have somehow limited visibility till some distance. So if will happen that we have one robot and other one is very far, then maybe we don't need to take care about that if they are visible between them, since the other one is very far. This is the reason, and this was a motivation to introduce the invariant mutual divisibility. Then mutual divisibility set is a set of vertices of graph G such that for any two vertices from this set, we have or they have distance larger than D, or these two vertices, for these two vertices, we can find the shortest path joining them, and that this shortest path will not contain any other vertex from this set. Of course, we are looking for the maximum possible cardinality among all mutual divisibility sets, and this cardinality we denote in this way, and we call mutual divisibility number. One example. If we will consider path which has 14 vertices, and we will think about classical mutual visibility set, then we will easily see that in this mutual visibility set can be formed only by two vertices. Because if I will try to add one more vertex, then we will have shortest path, which is unique here, which will contain one vertex from this mutual visibility set. The classic version we also obtain here in the case of mutual divisibility number when D is equal to the diameter of the graph, or more than diameter also, if we will consider. Of course, it's not necessary to study cases when D is more than diameter, but so in this case, if D is equal to the diameter of the graph, then we have a standard mutual visibility problem, and we are looking for the mutual visibility set. But interesting is when D is less than diameter of graph. For example, if D will be one diameter but one vertex, so will be only a little bit less, smaller than diameter, then we can see difference between mutual visibility set and mutual 12 visibility set. In this case, we can add one more vertex. Why we can add this vertex? Because we don't need to take care about visibility of these two leaves of the path. The distance between them is 13. So since distance is larger than D, then we don't take care if they are visible or not. If we will do smallest D, for the same graph, we will observe that to the mutual divisibility set, we can add more vertices. Here we can form mutual 11 visibility set for the path by 4 vertices. So now we can have some take some intuition that when D will be smaller and smaller, we can add more vertices to the mutual divisibility set, because then we don't need to take care about the vertices that distance between them is larger than D. So if we have smaller d, more vertices will have distance larger than d. Here we have example for d equal to 3, equal to 2. What will happen in the case when d is equal to 1? If d is equal to 1, then we only need to take care about our neighbors, and the path between neighbors has length 1. We have no any vertex in the middle. So for this case, mutual one visibility set always is formed by a whole graph, all vertices from the graph. As I mentioned, if d is equal to the diameter of the graph or greater than diameter, mutual divisibility set is the same, represents also a standard mutual visibility set. And I would like to do one more remark here about graphs of with diameter 2. We know that our large family, very big family of graphs of diameter 2. And if a graph has diameter 2, that means that mutual 2 visibility of graph is equal mutual 2 visibility number of a graph is equal to the mutual visibility the standard mutual visibility number. Here we have a chain of inequalities, what I mentioned before. When d is smaller, we can add more vertices to the mutual divisibility set. So here we have this kind of chain. I recall that when d is equal to diameter, we are working with the classic, with the standard mutual visibility set. And when d is equal to 1, we consider whole graph, all vertices of a graph, they form one mutual one visibility set. Now I would tell about a very important problem, Cerankiewicz problem, and I would like to show that there is a connection between this problem and mutual to visibility. First of all, as I mentioned before, if I have graph with diameter 2, then mutual to visibility number is equal to the mutual, to the standard mutual visibility number. This one we have here, because if we will think about Cartesian product of two complete graphs, this graph has diameter 2. So this is the reason that we have here equality. Moreover, it was shown that that standard mutual visibility number for classical for Cartesian product of two complete graphs is equal to the maximum number, to the Cerankiewicz number, which is the maximum number of ones such that binary matrix of the size m times n can have, and this binary matrix cannot contain submatrix of ones with the size 2 times 2. Here we have some example. If here we have Cartesian product of a complete graph, first factor has complete is complete graph with 4 vertices. Also, the second factor is complete graph, also with 4 vertices. And when we are looking for mutual visibility set, we can observe that this situation which we have here, these 4 red vertices, cannot be in the mutual visibility set. Why they cannot be? Because, for example, for these 2 vertices, we have only 2 shortest paths. One is here, and the second is here. So we observe that we don't fulfill condition of the mutual visibility set. We have no shortest path that will not contain other vertices from the mutual visibility set. If we represent these vertices by using matrix, binary matrix, and then we will we will put one when vertex belongs to the mutual visibility set and 0 when doesn't belong, what we obtain for this graph, if we will add these vertices to the mutual visibility set, we know that this one is forbidden. It's the same like in the Zarankiewicz problem. It's forbidden to have a submatrix 2 times 2 of ones. So here we see the connection with this concept with Zarankiewicz problem. As I mentioned before, in the case of classical mutual visibility problem and general position problem, we know that these two numbers are equal if we have graphs that for any two vertices in the graph there exists unique shortest path. So this is the reason now that I want to speak about the general deposition concept, because this one is the invariant of general position problem, where we also take care only about vertices from this general deposition set, such that the length of between these two vertices is at most d. So if the distance between these two vertices is more, we will not be worried what is happening, if they are visible or not. But if distance is at most d, we need to take care that for all shortest path, we will not have in all shortest path will not have other vertices belonging to the general deposition set. Of course, we are looking for the cardinality of a larger general deposition set. We denote this cardinality in this way. And since this condition which we have to fulfill in case of the general deposition set is more strict than in the case of mutual divisibility set, then we have this relation, because if we will fulfill condition for all shortest path, then we have there at least one shortest path without vertices from this set. And I introduce here, I speak here about this problem because with this concept we have direct results for a mutual divisibility number in the case of path graphs. This one was proved before, but in our case, this one is a direct consequence because we have no more than one unique shortest path between any two vertices belonging to Pn. In the case of cycle graphs, we have one case that we have to take care separately. If we have cycle graphs of even number, and we consider two vertices which are diametral, then we have the situation that there are two shortest path between these two vertices. So this part we consider separately, and it's easy to see that in this case mutual divisibility number for this kind of cycles will be equal to 3. Now I would like to present some general bounds for this parameter. General bounds are related with 3 different parameters. One of them is K-dissociation set. If we have graph G, then a subset of the vertices is a K-dissociation set if the following two conditions for every pair of vertices from this set are fulfilled. The condition first is telling that the vertices, they can be neighbors, or if they are not neighbors, the distance between them should be larger than k. And the second condition tells us that two vertices which belong to k dissociation set, they cannot have common neighbor also belonging to k dissociation set. This parameter is not too much studied. It's only studied in the case when k is equal to 1. And in other cases, no. Other parameter which we need to give the bound for mutual divisibility number is k-packing. K-packing is, we are looking for the subset of vertices, and the subset of vertices is k-packing if for any two vertices from this subset, the distance between them is larger than k. And we are looking for the largest k-packing of the graph G, and we denote by rho sub k of G. As we can observe, there we can find some relation between these two parameters. Here we have more conditions than here, but there, because of this distance, we can see that there is some relation, what after I will even show. And also we need one more definition here. We need simplicial vertices. Vertex is simplicial if its neighborhood induce a complete subgraph of G. And the set of simplicial vertices of a graph we will denote by this way. So if we will start to think about simplicial vertices in the graph, this is simplicial if we'll take set of all simplicial vertices. These vertices will form mutual divisibility set. Why they will form? Because if cannot happen that for any two vertices, simplicial vertex will be internal vertex of the shortest path. So with these three parameters, we obtain lower bound for the mutual divisibility number. The lower bound is related with these parameters. As I mentioned before, there is no the k-dissociation number is not too much studied. Only there are some works in the case when k is equal to 1. So we try to look for some bound for k-dissociation number, and we obtain the following results, that we can relate dissociation number, k-dissociation number, with the packing number. Packing number not of the graph G, but of line graph of graph G. I present some lower bounds, and now I will want to give some upper bounds. Here we have upper bound in the case when not for all G graphs, all graph G. Here we have the situation that graph G has guard at least with 5 vertices. So we cannot have in this graph triangles and cycle C4. In this case, we have this upper bound. And we have equality in the case when D is equal to 2, then mutual divisibility number of a graph is equal to 1 dissociation number of the same graph. We also obtain other upper bounds, since here we have one restriction, one condition, that graph need to have girth at least equal to 5. Here we have general bound for any graph G. And this bound is may be worst, but also are some examples that is tight. Here what we are doing, the upper bound, the general upper bound is to take all vertices of the graph and then remove vertices which belongs to the diametral path in this graph, and after observe a mutual divisibility number for this diametral path and add this number, and then we will have upper bound. As I mentioned, this upper bound is tight. Here we have some example. We have a graph. This graph has diameter 9. And then we can observe that for d equal to 3, we will have these vertices, black vertices, form the mutual 3 visibility set. And this number is equal to all vertices of the graph. Then we remove vertices belonging to the diametral path, and we add mutual 3 visibility number for this path. So we can observe that we need to add 6 vertices. This graph is not only one graph for which this upper bound is tight. If we will subdivide these two edges in the same way, we can subdivide by one vertex or more. Then also for this kind of graphs, we will have here equality. There are some more extra cases. I will not enter too much in this one. I would, since I see that I have still less than 20 minutes, so this part I will pass. I would like to show some results in the case of corona product graphs and lexicographic graphs. In case of corona graph, here I recall the definition and we have some examples. For corona graphs, we obtain exact values. Depends of the cases. If the second factor in corona graph is not complete graph, then this parameter is equal to the order of first factor times order of the second factor, multiplied by order of the second factor. If the second factor is complete graph, then we need to divide between two cases. If d is equal to 2, we have this value for the parameter, and if it's greater than 3, we have this value. We also were working with lexicographic product, and we obtained some results for this kind of graphs, some exact values. Here I recall the definition of a lexicographic product. To work with this product and to try to look for the mutual divisibility number for this product, we need some other results related with total mutual visibility number. So this was the reason that I was speaking at the beginning about this invariance. And also here we need domination number. So in the case of lexicographic product, we obtain exact values for all possibilities. But to speak about that, when we start to work about this with these products, we observe one interesting thing, that if we will take a lexicographic product, then for any graph G and H that will have at least two vertices, we can find the mutual divisibility set of, with the maximum cardinality, such that in each copy of H, we will need to add at least all vertices but one. So this one was a very important observation which we did it, and was very useful to obtain these results. The results, this parameter here, the results for the lexicographic products are also related with the domination number of the first factor. We can observe that if first factor has domination at least 2, that means that there we will not have universal vertex that is connected with all other vertices. We have this value. If we will find in the first factor universal vertex, so domination is equal to 1, then depends how look like the second factor, we will have one value for this number or the other one. The difference between them is only 1. At the end of this talk, I would like to speak about computational complexity of finding the mutual divisibility number. The problem which we have here is mutual divisibility problem, instance, a connected non-trivial graph G and an integer D at which is equal or greater than 2, and a positive integer k such that is less or equal of order of graph G. The question is, it is satisfied that mutual divisibility number of graph G is greater or equal than k? To speak about complexity, I need here to recall known decision problem, independence problem, and independence problem, it is known that is NP complete. So the idea to prove that mutual divisibility problem is NP complete, we did some reduction, polynomial reduction from this problem to this problem. I will show the construction, but construction for the one specific case when D is equal to 4. That will be easier to see the reduction. So we want, here we need to work with a rooted product graph, and some construction is like a rooted product graph plus one vertex here, which is joined with other vertices, but from the beginning. Here we can take any graph G. In this case, that will be easier to see. The graph G is a cycle with 5 vertices. Here is this graph. And then, since we have 5 vertices, we will take 5 copies of graph H. How we construct graph H? Graph H, first we'll start with path, which has 2D but 1 vertices. If we have D equal to 4, then we consider path with 7 vertices. Then we need to add 2 more vertices. When we add these 2 more vertices, we need also add 7 extra edges. The edges which we add is we connect these 2 vertices with the central vertex of this path and neighbors of this vertex. In this way, we obtain graph H. Now, what we will do a rooted product of G graph and graph H when the rooted vertex is where root is here. So what we are doing is we identify this vertex with one vertex from graph G. From the second copy, we also identify the same vertex with second vertex of graph G, and so on, and then we obtain the rooted product of these 2 graphs. But still is not the end. We need to add 1 extra vertex, and we need to join this vertex with all vertices from the graph G. Then we will obtain graph which we denote the G4. In this case, for this graph, when we will start to look for the mutual for visibility set with the maximum cardinality, we can observe that this set is formed by these vertices at the end. These vertices here, 3 here, 3 here, and so on. And with the vertices which belongs to the maximum independent set of the graph G. So finally, what we have is that mutual divisibility number of this graph which we constructed in general is equal to the independence number of this graph plus 4 times order of a graph G, because as we have seen, for each copy of graph H we took 4 vertices, and we have order of G copies of graph H. So with this one, we could prove that the mutual divisibility problem is NP complete. The results which I show are results for some families of the graph, but still is many things to do. Still is not known. For example, there are not studies of this parameter for the case of Cartesian product graphs. We have seen results for lexicographic product graphs, for coronal product graphs, but there is nothing about Cartesian product graphs, direct product graphs, strong graphs, and also generalized Sierpinski graph. Also, other open problem, what will be interesting to do is to try to characterize all graphs such that we will have this equality. And other more open problem, we can try to characterize all graphs when a mutual divisibility number is equal to the number of all simplicial vertices of the graph. As I mentioned before, simplicial vertices can form mutual divisibility set. Maybe will not be the biggest one, but they can form. So the idea is that we want to have all graphs when the mutual visibility number is equal exactly to the number of simplicial vertices. And since this parameter is related with the K dissociation number, it will be nice to study this parameter. As I mentioned before, this parameter is studied, well studied for the case when we have 1, and is called dissociation number, but there is nothing about the case when K is more than 1. So that's all from my part. Here are some references. Thank you very much for your attention.